In this next video, we're going to look at a two-sample separate variance t-test. So we have two samples or two groups that we've collected samples of, and we're trying to extrapolate to the greater population the averages for these two groups and how they compare. Now, this is different from a two-sample z-test because we don't know the variability in the population. And it's different from a two-sample pooled t-test because we don't know if the variability of the two groups are the same. We're assuming that they're different. Okay. All right. So when we do a two-sample separate variance t-test, we state the null and alternative hypothesis. And so just like we saw with the pooled t-test, you take the average for the group in the population, group 1, minus the average for the group 2 in the population, and then if are they equal? Are the two groups equal? So our null hypothesis is mu1 minus mu2 equals 0. Then the alternative hypothesis is they don't equal 0. Alternatively, you could have a one-tailed test. So we could say that, group 1 is bigger than group 2. So mu1 minus mu2 is greater than or equal to 0 for the null and less than 0 for the alternative, or we could go the other way. The null hypothesis mu1 minus mu2 is less than or equal to 0, and the alternative is mu1 minus mu2 is greater than 0. Remember, the null hypothesis always contains 0. The alternative hypothesis is what the researcher thinks. Now, it doesn't always have to be greater than, less than, or equal to 0. It could be that you think the difference is a certain amount, and so you're testing that the difference is a number. You think the difference is 5. You think the difference is more than 15. It doesn't have to be 0, but most commonly we are assuming that we're just testing, is there a difference? Is one group greater than or less than the other group? When it comes to a two-sample separate variance t-test, the test statistic looks like this. So we have a t-distribution here. We have the difference between the averages in the sample, x bar 1 and x bar 2. And then our standard error is the square root of the sample standard deviation squared, so the variance of group 1 divided by n plus the variance of group 2 divided by n2. Take the square root. The degrees of freedom here is a complicated calculation that's dependent on the variability in the sample. With this test statistic, there are assumptions. We are assuming random sampling. You really can't do hypothesis testing without that first assumption because you can't make statements about the population if your sample isn't representative of that population. Now, we assume normality. In order to use the t-distribution, we're assuming the underlying population is normally distributed. We can check those types of things with QQ plots. We are assuming the population variance and standard deviation are not known, and they are not assumed to be equal. So either we don't know or we know they're different. Okay? And we have independent samples. That is, the groups, the entities, the individuals who are in group 1 are not the groups or entities that are in group 2. A dependent sample, as we talked about previously, is where you have the same person, maybe it's a pre and a post. So we do an assessment or measure something, we give you a treatment, and then we measure or give you assessment afterwards. So you're in both samples in a dependent sample. In an independent sample, the people in each group are different. Like all other hypothesis tests, we can also create confidence intervals from them, and those come from rearranging those test statistics. So we take our test statistic that you saw above, we rearrange it and solve for mu1 minus mu2. And so you can see here our confidence intervals are the point estimate, here being the difference between the sample averages, plus or minus, and then we have our critical value from the t-distribution times our standard error. And that t times the standard error is, of course, the margin of error. So it's the point estimate plus or minus the margin of error. If we have a one-tailed hypothesis test, you can create a confidence interval that matches, that is the same tail. All right, let's give this a try. It's been reported that employment interviewers spend more time talking to applicants who are hired than to applicants who are rejected. To determine whether this is true for college students seeking summer internship, a researcher posing as an applicant accompanied a random sample of college students to their job interviews. A record of the duration and outcomes of the 49 interviews were kept. All right, so here, let's start with H0 and HA. What do we believe? We believe here that the average time for those who are hired is longer than the average time for those who are rejected. Okay, so writing that out this way can help you in terms of thinking this through, which means that our alternative hypothesis is that the average for hired minus the average for rejected is greater than 0. More time with those who get the job, which means the null hypothesis is the average hired minus the average rejected are less than or equal to 0. So then the next decision we have to make is, what is the level of significance? So let's assume that we're going to do an alpha of 0.05. Okay, then we need to create our decision rule. Here, it's a t-distribution. We are looking at the upper tail because we're looking at greater than. So this area here is 0.05. This is going to be our critical value, which is going to depend on our alpha and our degrees of freedom. And we are then going to reject the null hypothesis if our test statistic is greater than our critical value. So if it's up here, or if our p-value, it starts to get grumpy when I try to write off the screen and then it never recovers. If our p-value is less than alpha. Okay, so if we get a p-value less than 0.05, we will reject the null hypothesis. All right, let's do this. Start by Excel. We are finding our data set here. And what is this data set? This data set is not in this one, it is in Stats 1. So let me make sure I open the right one. All right. Loss, interview. Okay, interview. So here we have hired and rejected in our two columns. It is an independent sample because the people in this column are not the people in that column. We are going to, under data, do our data analysis. And just a reminder, under tools, you can do Excel add-ins if you have a Mac. Otherwise, if you're on a Windows, pick the tab to the left and do options and then select add-ons. We're looking for the data analysis tool pack. Okay. All right, data analysis tool pack, to sample assuming unequal variances. We need to identify the two variables. So hired is going to go first. And then we have rejected second. The order matters because it's how you defined your null and alternative hypothesis. And we are looking at a difference here of 0. And we're doing an alpha of 0.05. You could change this to 0.01 if you wanted to be 99% confident. So you could change that there. All right, so here we go. Make this bigger. All right, we get a test statistic of 0.9384. That is a big test statistic. And we have one tail and two tail. In our example here, we have greater than 0, so we are a one-tailed test, and we gave it an alpha of 0.05. So we are going to look at, is our test statistic more than the critical value? So let's look here. The critical value for a one-tailed test is 1.679, and our test statistic is way bigger than our critical value. So according to our decision rule, we reject the null hypothesis since the test statistic is greater than the critical value. We can also look at the fact that the p-value is 1.83 and see that e to the negative 12. That means that we would be taking, so just to kind of give you an idea of what is 1.83 e to the negative 12. Okay, what is that? That means we take the number 1.83, which has a decimal here, and we move it over. That's 1, 2, 3, 4, 5, 6, 7, 8. So all of these would be zeros. And we'd keep going, and we would move it all the way over 12 places. So you can see how teeny tiny this number is, because essentially there's 11 zeros in front of that 1. So it's 0.0000011 times until you get the 1. It's a very, very tiny number. So that negative says we're going to move the decimal place to the left. If this was a plus, if this instead said plus, then we would be moving the decimal place to the right. We'd be moving it over 12 places to the right, and it'd be a huge number. So when we look at engineering notation, you're looking at p-value versus alpha. So if you have e to the negative anything, that means your p-value is super tiny. All right, go back. So our p-value, 1.83 e to the negative 12, super tiny. Our p-value is less than alpha, and we reject the null hypothesis if the p-value is less than alpha. So we reject the null, and the average time of the interviews for those who are hired is more than those for the time who are rejected. Okay, we just did that in Excel. We can also do this in Python, so let's go about doing that. And just to remind you, for what will become the millionth time, you can work through these workbooks at drstephpowers.github.io/BIA. Go to hypothesis test under supplemental material, open it in Google Colab, which will open it in your Google Drive, log in, save a copy so that you can edit it, save a copy in your drive. You will also need the data sets, which you can find here under data, stats, and stats 2, or where we've been living. So you go here, you download it with that button there and save it, dump it into your Google Drive. And then when you go to work in this workbook, your first step here is going to be to import pandas as PD and to load your Google Drive. So linking your Google Drive and your workbook. So you run those two, run. It'll ask your permission to pick which Google Drive and all that. So then if we're scrolling down, we're under hypothesis test. We are doing the separate variance t-test. And now that we've loaded pandas and we have linked it to our Google Drive, we can now have it load in our statistics.xls file because we want that sheet that is called interview. So again, this part of the code here is where you've located it inside of your own Google Drive so that you can pull in your data set. And I've named this data set X7, call it whatever you want. So we'll call the data set X7. We'll take a look at the data set by using the command head. So we're applying head to data set X7. You see the first 5 rows. So we get those who are hired and those who are rejected. If we are doing a separate variance t-test, it is going to be the same package and same command as with the pooled t-test. The only difference being this equal variance equals false. Okay, so I'm going to, from skippy.stats, import t-test_ind. That's the same one you used before. Now in this particular data set, if I look at the original, notice that with this particular data, we don't even have the same sample size in the two groups. We have hired and we have rejected. So when I go and I run the code, I'm just going to pull this piece out here. When I go and I run the code, I get this, NaN. So there's obviously something wrong. Well, Python, a little quirky. It doesn't like the fact in this independence test when you have missing information or where you have two different sample sizes for the two different groups. And so what I'm going to do is use the command drop NA so that it says, okay, here's my list of the people hired. Here's my list of the people rejected. And what it had done is it had, in this rejected list, it had put NaN for these three what it thought were missing values, right? Because by default, it's thinking it's a table or a spreadsheet that has rows and columns and they each mean something. Well, here the rows don't mean anything because we have two independent samples. But in order to help Python deal with that, if you add in this command that says drop NA, then it will cut off that list and not have these sections in the list of values and not have this basically say NA, because it doesn't know what to do with those, right? So we're basically saying drop those when you look at each of these samples. Okay, so I've added this drop NA. Otherwise, it's test_IND. From table X7, I am going to pull the hired column, but I'm going to have it drop any empty information. And then I'm going to take from table X7 the rejected column. I'm going to drop the empty ones that are in it. I am going to do equal variance equals false because that was the difference between the pooled and the separate variance. The other thing here is that we need to decide one-tailed test, two-tailed test. And in our data, here we go, back to our alternative hypothesis. Our alternative hypothesis was hired is more than rejected, greater than. So we are going to go into our code and use the alternative greater. Okay, so now I'm going to run this and I should get some numbers. I get a test statistic that's 8.76, super big number. I get a p-value that is very, very small. And so in this particular case, I have a p-value less than alpha. And so I am going to reject the null hypothesis, and those who are hired spend more time in the interview than those who are rejected. Before we leave this, I'll just give you one more example that you can try. So here we have in Python a data that we're calling table 8. And so that data here, let's just go. The objective of a study by Baker et al. Was to determine whether medical deformation alters in vitro effects of plasma from patients with preeclampsia on endothelial cells and their function to produce a paradigm similar to the in vivo disease state. All right, not an expert in that field, don't know what any of that means. All right, so subjects were 24 pregnant women before delivery, of whom 12 had preeclampsia and 12 were normal pregnant patients. Among the data collected were the following gestational ages at delivery. Is there a difference in the gestational age at delivery for women with preeclampsia compared to those with a normal delivery? So our data here is preeclampsia and normal. So can you, using Excel, we're in the stats 2.1 here, gestation. Can you, using Excel, perform a separate variance t-test to determine whether or not there is a difference? Now notice in this particular data set, I have actually changed the name of the column from normal to norm delivery. And that's because in Python, the word normal tells us normal distribution. And so that name is kind of protected already. And so if I entered the data in where the column or the variable name was normal, it doesn't like it and it won't perform my tests. So I have changed the column here to norm deliv, just so it's not the word normal. So something to consider if you're running code in Python and you're getting some errors. We talked about some of the quirks like dropping the NAs. Another one is there are protected names that have important meaning. And so because of that, you can't really use them for other things. So here we have in Python, we've imported in our gestational sheet from statistics 2. We have here our summary of the first 5 rows. Can you then do the separate variance t-test to determine, is there a difference in gestational age at delivery for women with preeclampsia compared to those with a normal delivery? So do we have a two-tailed or one-tailed test? Is there a statistically significant difference?